Welcome to the Explainer. Today, we're going to pull back the curtain on the internet. We're going to follow a single piece of your data as it goes on this wild journey, from your screen, across the world, and back again, all in the blink of an eye. You click a link and boom, the page is there. It feels like magic, right? But behind that single click is an incredibly fast, complex, and surprisingly organized trip. So let's dive right in. Here's the thing. It's not magic, and it's definitely not chaos. This journey is actually governed by a really precise set of rules, or protocols, and they're all neatly organized in layers, which we call a protocol stack. The best way to think about it is like a super efficient factory assembly line. Each station, or layer, has one and only one specific job to do. It's a classic divide and conquer strategy, and it's what makes this incredibly complex task of global communication totally manageable. Okay, so this table right here, this is basically our roadmap. Now, you might hear about the 7-layer OSI model. That's kind of the textbook theory. But we're going to follow the 4-layer TCP/IP model. Why? Because that's what the modern internet actually runs on. We're going to follow a piece of data on its way down this stack. So let's start at the very beginning. Our journey kicks off right where you are, in your web browser. This is the application layer, and it's all about how you interact with the internet. It all starts here. You type in a web address and you hit enter. What just happened? Well, your browser, the application, just created a message. It used a protocol, probably HTTP, which is really just a polite way of saying, hey server, can you please send me the content for this web page? But wait, there's a little problem. The internet doesn't run on names we can read. It runs on numbers. Computers need a very specific IP address to find anything. And that's where the domain name system, or DNS, comes in. You can think of it as the internet's giant phone book. Its entire job is to translate that human-friendly name into the numerical IP address the network actually needs. All right, so we have our request, and thanks to DNS, we know the exact address it's going to. The next big question is, how do we send it reliably? That brings us down to the next layer, the transport layer. You know, just sending a whole web page in one giant chunk is a terrible idea. It's way too risky. What if just one little piece gets lost on the way? The whole thing could be useless. So the transport layer's job is to break our request into smaller, more manageable chunks and get them ready for a safe trip. Now, for something like a web page, you need every single piece to show up, right? You can't have missing paragraphs or half an image. That's why we use TCP, the Transmission Control Protocol. It's like sending a package with a tracking number and delivery confirmation. The other option, UDP, is more like just tossing a handful of postcards in a mailbox and hoping for the best. It's fast, sure, but there's no guarantee. For our web request, we need the reliability of TCP. But before TCP sends even a single byte of data, it establishes a stable connection. It does this with a neat little process called the three-way handshake. It's basically a quick conversation. Hey, are you there? Yep, I'm here and ready. Great, I'm starting to send stuff now. This makes sure both sides are perfectly in sync and ready to go. And this is where our assembly line analogy really clicks. We've just put our letter, the HTTP request, inside a secure numbered box called a TCP header. This new package is now called a segment. And this process of adding a header, of wrapping the data, that's called encapsulation. You're going to hear that word again. We have a securely packed box, but where in the world is it supposed to go? That's the all-important job of the next layer down, the network layer, or, as you'll often hear, the internet layer. This is where the famous Internet Protocol, or IP, comes into play. The network layer basically slaps a big mailing label on our box. It writes the full destination address and the return address right on the outside. This IP address is what allows routers all across the globe to figure out where to forward our data. To make this all work, every single device connected to the internet needs a unique IP address. The classic system, IPv4, gives us about 4.3 billion of them. At the time, that sounded like an infinite number. But with all our phones, laptops, smart TVs, and who knows what else, well, we've basically run out. That's a story for another explainer. So now our secure box, the TCP segment, is put inside a mailing envelope that has the full address on it, the IP header. This complete unit, ready for its global journey, is now officially called a packet. Okay, our packet is addressed and it's ready to cross the world. But how does it make that very first hop? You know, from your laptop just to your Wi-Fi router sitting a few feet away. That's the job of the link layer. This layer doesn't care about the final destination in another country. It's only focused on the local neighborhood, on getting the data from one node to the very next one. And for that local trip, it uses a completely different kind of address. It's called a MAC address. This is a unique hardware identifier that's literally burned into your device's network card. So if the IP address is like the street address for a giant apartment building, the MAC address is your specific apartment number. It's how devices on the same local network, like your router and your laptop, find each other. So our addressed envelope, the packet, is now handed to the local mail carrier, who puts it in one last pouch for local delivery. This final wrapped unit is called a frame, and this is what finally gets converted into the actual physical signal, the electricity in a cable, the radio waves for Wi-Fi, or the pulses of light in a fiber optic line. Whew, okay, let's just take a breath and recap. We've just followed a simple click as it got dressed up, layer by layer, getting prepared for its journey. Let's quickly walk through that layering process one more time. This process, encapsulation, is the absolute key takeaway. It starts as data, the transport layer wraps it into a segment, the network layer wraps that into a packet, and the link layer wraps it one last time into a frame. It's like a set of Russian nesting dolls. Then, once it arrives, the receiving computer just unwraps all those layers in the reverse order to get back to the original message. It's an incredibly elegant solution. And really, this layered design is the secret sauce of the internet. It's what makes it so incredibly powerful and resilient. It means we can invent a whole new technology, like 5G at the link layer, and it doesn't break how your email works at the application layer. Each layer can evolve on its own without bringing the whole system down. And that leaves us with a pretty fascinating question to chew on. This elegant system, designed over 40 years ago for reliability and scale, absolutely delivered. It's what allowed a small research project to become the backbone of our modern world. But is it ready for what's next? In an age of AI, quantum computing, and billions of connected devices, is this still the right architecture for the future? What will the next digital world be built on?